Hey, welcome back. Today we're going to be talking about how to solve physics problems with both translational and rotational kinetic energy. So this is for AP Physics C mechanics students, but it's also for AP Physics 1 as well as just physics students in general, like high school physics students. There's no reason why you couldn't see problems like this, and there's no calculus involved here, and I'm going to talk you through it. So let's go ahead and get to it. I don't want to read at you, but I'm just going to point out some of the things that are important about this problem. First of all, there is a height difference here. Whenever you see something like a ramp with a height difference that's going on, I want you to think in terms of energy if there's a height difference. That's not always a conservation of energy problem, but the vast majority of these style problems that you're going to see with a height difference, it'll be a conservation of energy problem. The other thing that we want to do at the outset with a conservation of energy problem is mark where our axis, where our height is going to be equal to 0. And we want to do that in such a way as to simplify the problem, of course. So if we set our height equals 0 right about where the center mass is for the lowest position for the object, like wherever it's lowest is going to be your height equals 0, then that'll help simplify the problem. Here, this will be our initial position for the sphere as it rolls down. I do want to point out for this problem we have 5 options for our answer. And this right here is a little bit different about this problem too. They've got the rotational inertia just as I, so we have to put our answer in terms of I. We're not going to break it down any further like we would typically for a problem like this. Importantly, when you see this phrase, rolls without slipping or rolling without slipping, something along those lines, I want you to think in terms of this small but mighty equation here that you can use for problems like this. And the big idea with this equation is you can convert from linear variables into rotational variables and vice versa. So whatever you need, you just take a look at what the problem is asking of you and you can convert back and forth between the two. Alright, so let's go ahead and get to it. We know that this is a conservation of energy problem at first glance because there's a height involved and we're not being asked specifically for friction and so on. So we're going to ask ourselves, what form of energy is the system in at the beginning of this process? Well, it's in gravitational potential energy, right? And what form of energy do we have at the end of this process? Well, we've got 2 types of kinetic energy. We've got rotational kinetic energy and we've got translational. That's also called linear kinetic energy, right? So just moving from point A to point B, rotational kinetic energy is the idea that the sphere does have rotational kinetic energy. So let's write down what we know about this. We know mgh naught is equal to 1/2 I omega squared plus 1/2 mv squared. So we know this is true, and we can't break down this I value any further. If we could, we would probably be able to cancel out the m's, but we cannot do that here. We are looking for this, and so because we are looking for v squared, we want to take that omega and turn it into a v squared. So what we're going to do is take this equation right here and solve for omega. So we could say omega is equal to v over r. And we're going to take that and sub it in over here. And so you could say this is mgh naught is equal to 1/2 I, and then our omega squared becomes v over r squared plus 1/2 mv squared. Alright, so what do we notice? Well, we are looking for this v value, right? So we want to get v. Notice we have v squared in both terms. So we can start by just factoring out that v squared and see what happens. So you've got I over 2r squared down below, plus our next term you've got m over 2, and that's what we're left with. Okay, and so next up, what do we want to do? Well, again, we want to get this v by itself, and so we're just going to divide both sides by that and see what happens. So we can say v squared is equal to... Okay, and so that's what we have. Now notice in this situation we've got a denominator with a denominator, and in that case you've got 2 in both cases, and so we can just do a little simplification with algebra and say, well, that 2 is the same thing as being in the numerator. So we can say mgh naught over, and we end up with this here. Okay, so we're getting closer, but notice we still have a fraction within a fraction. We've got that r squared in the bottom. We really don't want that. We don't want to have r squared in the bottom, and we want to be able to collapse that fraction if at all possible. So one thing we can do with just our basic algebra is to say, well, what if we multiplied r squared in the bottom and r squared up top? That is allowed, right? It's like saying I could move it over here just so you can kind of see the idea. This is the same thing as multiplying by 1, right? I could clean this up a little bit and show you what I'm talking about. So this is equivalent to taking what we have here and multiplying by 1. And if we do that, then we end up with this. And notice we have the I plus m down below. Oh, I can't forget this r squared down below here. But notice that the r squared again follows that pattern of, in algebra, if you have a denominator already in a denominator, that's the same thing as being in the numerator. So what we're going to do is take that and move that r squared up top here. And this is what we have. This is where we're at. And again, we want to start looking over and glancing at our different options. A, B, and C are clearly not what we're looking for. If you look at D, that's looking pretty close, but notice that E is actually going to be in the ballpark of what we need. We just need to take one further step to be able to get this, and I'm out of room, so I'm going to write this going from right to left, so to speak. So I'm just going to write V is equal to the root of what we had before. And if we take a look at what we have, that actually matches with E. So E is going to be our correct answer. That's how to think through it. One slight issue that I would notice at the end of this problem, and go back if this was an FRQ, notice throughout this I was using little m based on habit. What I would do is probably go back and rewrite capital M for this, just to make sure I don't miss any points along the way if I was doing an FRQ. But that's how you would go about doing a problem like this. I've done screencasts on an entire year of physics and almost an entire year of AP Physics C mechanics. If you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.